as you like.
Yes. Yes, Roberto.
Okay. Hi, everyone. Good afternoon. It's a pleasure to introduce Professor Boumediene Chentouf from White University. Professor Boumediene is a full professor in White University. He received his PhD from University de Lorraine and at the University of Metz in 98 from France. Professor Chentouf's research focuses on the mathematical analysis of this specific equation, particularly well-posedness and stability, with special attention to the problems involving time delay and memory effects. Professor have a lot of papers and very important contributions included with our group from Recife. And it's a pleasure for me, Professor, to be here and enjoy this nice talk about exponential stability and of a non-local microbeam system. Thank you, Professor.
All right. Thank you so much for the nice introduction, Roberto, and also for the invitation. It's my pleasure to talk to you today. As you can see the title, Exponential Stability of a Non-Local Microbeam System. This is joint work with my colleague from Tunisia, Saber Mansouri. So the talk will be divided into basically 4 parts. As usual, the first one is just some introduction. Then I will move to the well-posedness of the problem, how to prove that the solution exists and are unique. Then after that, we will see how to prove the stability of the solutions of the system. And at the end, I will talk about some future problem and related to our system. So usually a beam is governed by what we call, or what's so-called the Euler-Bernoulli equation. Okay, but it turns out that for specific cases, like electrostatics excited microactuators, and also in micro switches, vibration shock sensors. In all these domains and areas, the usual and others like atomic force microscopes, in all these domains, the usual mechanical models are not anymore true. So that's why after that, I mean, people started using other types of equations, and now it's so-called microbeam system. Okay, these microbeam system or equations are now it's another way to present and explain the vibrations of certain types of beams. But as you can see from the title, is micro, so it means that it's very I mean, the thickness is very small, is in microns or even sub-microns. So many papers after the model came out, many papers and research articles appears from different perspectives, engineering, math, and so on. But as mathematicians, we are going to focus on this area, the control theory or control of microbeam systems. And I will not talk about the literature review, because I think it's time for half an hour, 40 minutes is that's not possible. So what I will do, I will just say that many results on controllability, observability, and stabilization appear in literature. And recently, with my colleague from China, Fang, we proved for the first time that this system can also be stabilized even in the presence of a boundary or interior time delay control. So this is to my knowledge, this is the first time that this system is taken into account the presence of a delay. Now, after that, we ask the natural question: what happens if there is a memory term in this system? And we started with the first case. This is the objective of my talk. The first case is when we have distributed or interior control in the microbeam system. So why local and non-local? So this is just a very short introduction. Usually local PDEs, which is classical PDEs, the state variable depends only on a specific point, xt. Usually, in our case, t is the issue. In a sense, I will explain it. But in non-local PDEs, the situation is different. In this case, the PDE, non-local PDE, incorporate information from different locations within the domain. And usually this situation arises when we have integrals, and call it most of the time memory integrals. And needless to say that in practice, non-local PDEs are naturally abundant. So you can find plenty of non-local PDEs, and that's why in our case, this is the system. The non-local term is here. That's the most important part. Is here. This is the non-local term. So usually, if A1 is 0, you ignore it. So it's 0 here. This is the classical microbeam system. So it's basically a second order PDE in time and sixth order PDE in space variable x. And we have now this is the PDE replacing the classical one earlier, where you have only the fourth order derivative of u with respect to x. So the u here is the deflection of the beam, and the extra thing is the non-local term, as I said. Okay, and you have 6 boundary conditions and 2 initial conditions. Okay, displacement and the velocity at time 0. And you have now the third initial condition related to this non-local term or the memory term in the system. The physical description of the system is maybe for the time being, we are going to say that rho is a positive constant. So this is the rho. A is the cross-sectional area, and L is the length of the beam. Usually it's in micro unit, or even smaller. And M1 here is a positive constant. M2 again positive constant. A1, you can assume A1 is 1. It's included in this function psi. I'm going to describe what are the properties. And M2 is another positive constant. So all these are positive constants in our case. But what is important is this memory kernel, the function psi. And of course, this is infinite memory term, because usually in some cases the non-local term is in bounded interval of s, like tau 1 to tau 2, and here we say that the memory term is finite. That's not the case here. So the case is infinite memory. Okay, and this is now the properties we assume in our case for the memory kernel Xi. So we assume that Xi is L1 integrable, is in H2, but we can assume that it's just C2, and the total mass is positive. The function Xi is non-negative. Its derivative is negative, so it means that Xi is decreasing, and we have this this property, which is basically we are saying that the derivative Xi prime decays exponentially. This is quite restrictive, but you can find in literature more general conditions. But for this talk, I'm going to take the simplest case. This is basically the simplest setting for the memory kernel Xi. So again, this is my system. This is the memory term, and that's why the system is called the non-local. Now, what we do after that, we are going to introduce this new variable, which is called the minimal state variable, and it's a new variable called omega, which is minus Xi prime. Remember that Xi prime is negative, so this will give you a positive here, and the difference of uxt minus tau and uxt. Okay, so this is the new variable. Okay, now you have plenty of functions satisfying Xi. We make sure that Xi exists, satisfying H1 and H2, and the simplest one, a typical one, is just the exponential minus positive constant C times S. So this is the typical example. The second important remark is the approach. This is called the approach is called the minimal state approach, contrary to the usual one, which is called the history approach, due to the famous work, the pioneer work of Duff-Hermos in 1970, where the new variable actually replacing here in our case is omega. The usual one in the history approach, you take the difference, only the difference of uxt and uxt minus s, which is here. Okay, but it turned out that this approach is fine. You can deal with the problem, but there is a drawback for this approach. I'm not going to go into details regarding the drawback, but basically the first one is we need the information of the information of u for negative s, but also it turned out that two different initial conditions will lead to the same solution, which is not very physical. I mean. Usually two different initial conditions will provide two different solutions. But for the history approach, if you use this history approach, you can find the same solution from two different initial conditions. Now, after that, once we choose this variable, the new one, the good thing and the good thing here, the non-local character of the system will disappear. Why? And this is the setting of the problem. So because of the boundary conditions, so these are coming from the homogeneous boundary conditions. Let me go back rapidly. So you see you have u0, u sub x at 0, and u sub x at 0. So the second derivative at 0 is also 0. So we pick up all this boundary conditions in one space, and it will be called the space V. And after that, we introduce the new space S, which is related to the new variable omega. Okay, and this is the condition. So it's the set of all omega in H1 L plus coming down to L2. with this integral is negative. So you remember that psi prime is negative. So here my minus psi prime is positive. So it makes sense. And we assume that this quantity is finite, and the inner product in S will be this one. So it's very simple one. It's just the derivative of omega t, two elements in S, and we take what? We take the product, and we multiply by 1 over minus psi prime to be positive, and we integrate from 0 to L and 0 to infinity, because omega is a function of x and s. I remember that S is from again, yeah, S is belonging to the interval R plus, so it's a 0 to infinity. So after that, we can prove that the kernel function psi at infinity is 0, and the minimal state variable, the new variable omega, at infinity is also 0. But the good thing, and it satisfies this PDE. So the derivative of omega at t is the derivative of omega at s, the derivative with respect to s, sorry, minus psi, which is the kernel, and ut. And the u is what is our variable. I mean the beam deflection. So what does it mean? It means that the new variable, called the minimal state variable, is satisfying a PDE, and our system, I will move directly to the system, yeah, can be written in as a Cauchy problem. This is just a differential equation in our space. I will go back. This is a Cauchy problem governed by the operator A, okay, and A is defined like this now. So you see that the v is just the velocity. The second row is just the PDE. You see the 6th order, the 4th order, but you have the extra term coming from what? Coming from this new variable omega, and the third part, which is the differential equation of omega. So we said that omega, the derivative with respect to t of omega is derivative of omega with respect to s minus psi u sub t, which is the v. Okay, so what does it mean? It means that the non-local character through this introduction of new variable omega is not anymore in the system, and this is the advantage of the minimal state variable, contrary to the usual approach, which is the history approach. So the space is the v for what? For the u, the L2 for the velocity. So this is displacement, this is the velocity, and this is the variable omega. So after that, we define the inner product. We make sure that it's actually in a product that I have my Hilbert space. And after this, we can start the machine. So we can tackle the problem of well-posedness and stability. For the well-posedness, so the well-posedness, we prove that as usual A is the operator A governing the differential equation in the Hilbert space H is dissipative and maximal. So we can prove that even for lambda is 0, that's true that A has an inverse. So we prove that the operator A is undissipative, and we can apply the semigroup theory. So this is the first result. So just through integration by parts, basically, as usual, we prove that the A is dissipative because you have v squared L minus A2, which is the positive, so this is a negative term. So what is this? This is just the velocity at L. And these two extra terms are coming from the variable omega, which is our minimal state variable. But these two terms are non-positive because psi prime, we assume that psi was decreasing, so this is negative, and the psi double prime, so the second derivative is positive, but with the minus here and the square here, so everything is negative. So my operator is dissipative, and after that we prove that it's maximal as usual. We end up with solving elliptic equation. So this is the setting of the equation. Lambda I minus A at UVW is FGH. So given FGH, we want to find UV and W, and you can see what here. This is the third equation. We can solve it to get that. This is simple, but we make sure that this element is in our space S, of course. And after that, because I need the the omega at 0, so I can get my omega 0 from here. I plug it here, and we end up with what? We end up with the elliptic problem with our boundary conditions. Okay. So usually, because the problem is linear, so this is quite simple. We can apply Lax-Milgram theorem. Okay, because we can look at the problem now. This is bilinear form, and this is the linear form. So we prove that the conditions of Lax-Milgram are satisfied, and we deduce after that the solution of my elliptic problem exists and is unique. Once we get U, we are done, because we already have omega, and the V can be obtained from the first equation, of course. So this is quite standard. Okay. So after that, we can conclude that the problem is well posed in the sense of semi-groups theory. The third part is about the exponential stability. So what happens to the solutions? This is the quite natural question. What is the long-time behavior of the solutions of the system? So first of all, we define the energy norm. This is basically the norm of U and UT. Okay, and this is the norm of omega in our space S. So this is the energy norm, and we can prove that the solutions are exponentially stable. In other words, the energy is decaying exponentially for any initial condition in our space H. All right, and this is phi naught. So actually, to prove the theorem, you have two methods because the problem is linear. So you have the first method, which is usually simpler, but it's involving calculations and a lot of computation, which is the resolvent method, or called the frequency domain method. The second method is the energy method, or Lyapunov method. So what we did here, we adopted the second one, which is the Lyapunov method. So what we do, we consider the new energy or perturbed energy, capital F, which is the classical energy of the system E, plus a perturbation, which is epsilon V, and epsilon here is a positive constant to be chosen. The V is the usual multiplier, is the integral from 0 to L x u sub t u sub x dx. So this is quite standard, even for the classical Euler-Bernoulli equation, heat equation. So this is very, very standard. And it turned out that things work very well in our case. Okay, even if there is a non-local term in the system. So first of all, we usually what we do, we try to find differential inequality for F, and then we deduce the exponential stability of E, because basically E is equivalent to F. So inequalities in two sense. I will show it later. But for the time being, what is derivative of this extra functional v? Okay, so you see that you have many terms, of course, but what is unknown here is the first term here and the last one. So this is cross product of u sub x and the omega, and another cross product of u sub x u. So we don't have a control on these two control of sign, of course, on these two terms. For the others is okay. Whatever positive or negative, we can have a better control. So of course for the negative terms, that's fine, that's good. This is a good guy, this is a good guy, this is also a good guy, this is not bad guy, but at least it's a square, so we are going to control it with another square. This is a good guy, but the issue is the first and the last term. So what do we do as usual? We use Young's. Okay, this is Young inequality. For this is the last term. For the first term, what we are having here, u sub x, u sub t at L. So we use Young, but still have ux sub squared, u sub x squared, u sub t squared at L. But we have Wirtinger inequality, which is we can call it Poincaré inequality. So it's more accurate. You have the constant here is known. Okay, although it's not the best one, but at least we have it here, and we use it to control this term with the second derivative. Okay, so this is for the last term, last bad term here. And now after that, for the first term, again, you end up with this one, and this one again, we can control it with this integral. Why? Because of the boundary conditions. So this is true because u sub x is 0, u sub x at 0 is 0, u sub x at u at 0 is 0, u sub x at 0 is 0. So these two conditions are true, so you can apply this inequality. Okay, so you control this with this the L2 norm of u sub xx. So after that, if you plug all this in our derivative of v, you end up with this. Okay, so this is the extra, this is 1. This is u sub xx was there, but you have extra, which is these 2 here, coming from Young's inequality. This is also extra term. Okay, I'm sorry, this is a plus here. I think there is a typo here. It should be a positive here. Yeah, it should be a positive. So it should be a plus here. And after that, we go back to the derivative of the energy, which is just the dissipation of the energy. It's like this. So you have these 3 negative terms, and we go back to our functional f, which is the derivative of f will be derivative of e plus epsilon derivative of v. So you have the derivative of v, you have an estimate is here, and you have the exact value of the derivative of u. You plug them, you end up with this one. So collecting all these terms, okay, you end up now with good terms and bad. What are the? This one we can control it, the first one, because the extra parameter epsilon can be assumed to be small, so we can choose it so that this coefficient is negative. This one is okay, all these are okay, and again this one, okay, we can control it through delta 1 and delta 2. So delta 1 and delta 2 are coming from where? From Young. So these are arbitrary constant, the for delta 1 and delta 2. So here we control this term here to have it negative. The coefficient is negative by choosing delta 1 and delta 2 small. And now we have a problem. The only problem is here. You have this term and this one are positive. This one is fine because remember that we assumed that the second derivative of the memory kernel is positive. With this minus is negative, so it's fine. It's fine. This term is a good guy, but this we said that here we can control, but we have here these two terms are positive, which is the problem is here. So how to control this? Here we just use the property or the condition H2. This H2 cannot was not used before. I mean, for the well-posedness of the problem, we don't need it. Now this is the condition H2 plays here a crucial role, so that we control these two terms. So what we do, these two, okay, one is here, okay, and our derivative becomes like this now. So the two terms are here. And of course we said that this one is negative, so we can ignore it. Okay. So what we do after that, we can prove that by the choices that the derivative of f is minus positive constant nu or ET, and ET is the classical energy. Okay, knowing that this new energy or the perturbed energy is almost the same as ET, so it's equivalent, this differential equation will give us the exponential stability of the classical energy ET, and we have an estimate of the decay rate. Oh, I'm sorry, this should be here. I just realized this one. Yeah, of course. So you have the estimate of the decay rate, which is here, and this is the constant. Usually we call it m. So what we are proving that ET is less than or equal to m exponential minus alpha t E0, and the alpha is this constant here, minus nu over 1 plus epsilon c1. And this concludes the proof of the exponential stability. Of course, we took initial conditions quite regular, like in the domain of A, and through the classical argument of density, the result will be extended to the whole space H. So this is quite standard. I will end up with a small comment. So as you can see, we proved that despite the presence of the non-local term in this micro beam system, we proved that the solutions are decaying exponentially by using the minimal state variable. And the more difficult case, okay, to be considered, hopefully next in future, is when the non-local term appears in the one of the boundary of the problem. But this is more challenging because usually it's more difficult to control the non-local term in the boundary than when it appears in the equation. This is quite common. So these are some references. Okay, most of them are just motivation of the model. So all this except the second one, where, as I said, we proved that the the system is also exponentially stable, but under the presence of a delay in the boundary or distributed. Thank you very much for your attention. That's it. So this is the end of my talk.
Thank you, Professor Boumediene. Right now we will open for questions or comments. Please, if you have some questions, comment, can do it now. Questions, comments? Boumediene, can you show again your system, please?
Sure.
Roberto, the
Yes.
problem with this line?
No. I just have a question.
Yes,
A comment. Okay.
Yes. You can see it?
Can I see your, yes, right now here. Do you have some results if you consider the system of plates or something, system of beans or something like that, using this kind of a delay? You have some reference that some results with when you consider two equations?
Two systems?
Yes.
Two systems, you mean that is coupled? You mean you couple
Yes.
the
coupled
beam
system.
with some? Yeah, you can. Of course, I'm sure that it works, but we didn't consider this problem. But I think that the method is so strong. You can couple this beam with for example, a heat or sort of ODE, for example.
Yeah,
you can because the difficulty is not the system. The difficulty is here. I mean,
Okay.
the non-local term of this part here. So the difficulty is. So you can consider couplet system. We didn't consider this so far, but I'm sure that it works.
Okay, nice. So if some question or comments, if not, let's say thank you, Professor Boumediene. Thank you, Professor.
Thank you.
So I have just an announcement. Next section will be June 25. The speakers is